Welcome back to my class. So, in today's class we are going to learn about resource allocation and binding. So, if you look back to this high level synthesis, we have learned that high level synthesis consists of several subphases. Initially we do pre-processing, followed by scheduling, allocation, binding, data path generation, controller generation, and then finally we will get the RTL, right. And we have in the previous few classes we have learned about scheduling. So, once the scheduling is over, we are going to do the allocation and binding, right. So, scheduling assign the timestamp. So, we know how many clock cycle we need to execute the complete behavior, and we know in every clock which operation is going to execute, right. So, what is our next task? Next task is to make sure that in the hardware these operations are going to map into FUs and the variables are going to map into registers. So, that is what I have to allocate sufficient number of registers and function units, so that I can map this variable to the registers and operation to the function unit, and which actually satisfy the scheduling requirement. I am not going to change the requirement what we have done in scheduling, right. So, if you look into this allocation and binding problem, that I am going to map the operations to the function units and variable to the storage as I mentioned here. And what is our objective? Objective obviously in the hardware I want to use minimum number of resources, right. So, what does it mean? I want to use as less as possible function units to execute all the operations in the behavior. Similarly, I want to use minimum number of storage, which is basically register or RAM, ROM, to store all the variables and arrays of the program, such that the overall use of this registers and function units is minimum. And how we can achieve that? Obviously, you have to share that, right. So, unless you share, if you have each function unit is allocated for each operations, you will not get any savings, right. If I can do that, two operations can be executed by a single FU, or say two variable can be stored into a single register, then I am having a saving. So, I want to maximize this resource sharing, right, and hence minimize the resource usage. So, that is our objective, right. So, I want to maximize the resource sharing and hence minimize the resource usage. And this allocation and binding faces two subtasks. It is clearly understood that because operation has to be mapped to function units and variable has to map to the storage. So, it has two completely separate subtasks. One is FU allocation and binding and register allocation and binding. Here by register I want to mean the memory which consists of both register and as well as memories like RAM and ROM. Okay. So, we are going to discuss first this FU allocation and binding, and then subsequent classes I am going to discuss about the register allocation and binding. Okay. So, as I already mentioned that this allocation is something you identify the minimum resource required, and sometime if it is a resource constant scheduling, then we already know the resource available for me, right. So, we already have seen that for scheduling, that if you have only 2 multiplier available or 1 ALU available, right. So, once that is given, or you identify what is the minimum requirement, right. So, that is what you allocate sufficient number of FUs, and then binding is basically map this operation to FUs and map the variable to registers, right. And our objective is to sharing. We want to share one FU for multiple operations, and similarly I want to share one register for storing multiple variables. Okay. So, that is our objective. So, now let us only concentrate on the function unit allocation and binding problem. So, if you look into a schedule graph, which we have taken the example that we consider for our scheduling discussion. So, this is the schedule behavior that in time 1 I am going to execute these behaviors, these operations. In time 2 I am going to execute these 3 operations, time 3 I am going to execute these 3 operations, and in time 4 I am going to execute 5 and 9, right. And here you see there are 2 multiplier and 1 addition operation is scheduled in time 1, right. And similarly, 2 multiplier and 1 less than operation is scheduled in time step 2, and so on. So, once I am going to identify the total function unit requirement, I can consider these multipliers separately from others operation, because once I try to find out the minimum requirement of multiplier, I do not have to consider how many adder is needed, how many other type of function units is needed, right. So, the important point to be noted here is that once I am going to consider about this function allocation and binding, I can consider the operations independently. Okay. So, it means I will consider only multiplier allocation binding. Once I am done, I will take this ALU allocation and binding, because we have seen that ALU is kind of operation, I mean a function unit which can do addition, subtraction, greater than, less than operations, right. So, once I am going to do multiplier, I am going to do it independent of these other operations. When I am going to do ALU allocation and binding, I am going to do that independent of the multiplication or other operations, right. So, this is something is the decomposing the problem into each type of operator, and then you do this analysis to find out the minimum requirement, and then you bind the operations and then go for the next type of operation. Okay. So, now we are going to discuss how we can solve this problem, and we are going to show that in next few slides that this particular FU allocation and binding problem can be mapped to either graph coloring problem or clique partitioning problem, right. So, let us understand that. So, let us understand what is compatibility. Okay. You consider a simple schedule behavior like this, where I am, because I am taking only one type of operator at a time, here all I am considering only the operations that are of type plus, right. So, all operations are having plus operation, right, and assume that in time step 1 this operation 1 and 2, this is operation 1 and this is operation 2, this is operation 3 and this is 4 and this is 5, right. So, in operation time 1, operation 1 and 2 is scheduled, in time step 2 operation 3 and 4 is scheduled, and in time step 3 operation 5 is scheduled. Okay. So, what is the compatibility? Let us understand that. So, since this operation 1 and 2 is scheduled in time step 1, you have to have two different FU, right, to execute these two. So, they are not compatible to each other. So, they are conflicting each other, right. So, they has to be allocated to different FUs, right. Whereas, this 1 and 3, since they are actually executing in different timestamp, so I can execute both the behavior, both the operations using a same type of, using a same FU, right, so same ALU, because in time, so that ALU will perform this operation 1 in time step 1, in the next clock in time step 2 it can do operation 3. So, that means once these two operations are scheduled into different timestamp and they are of same type, then they are compatible to each other. Understood? So, from that I can actually construct a graph called compatibility graph. Okay. So, if you take this behavior, then what will be the compatibility graph? In the graph, you know, you have to find out the nodes, and the nodes are the operations. Since there are 5 operations here, I have 5 nodes. Okay. And what are the edges here? Edge defines the compatibility. If two operations are compatible, just we have discussed, we will have a edge, right. So, when they are compatible, when the operations are of same type, all are addition operation, addition or subtraction operation, ALU operation, and they are scheduled in different timestamp. So, I have so for with 1 3, 4 and 5 is scheduled, because they have not scheduled in timestamp 1. So, from 1 I have it is to 3, 4 and 5, but I do not have a edge from 1 to 2, because they are running in parallel, right. Similarly, from 2 I have edge, I should have edge to 3, 4 and 5, because they are compatible to 2. So, I have edge to 3, 4 and 5, and for this operation 3 I have already, so 1, 2 and 5 is compatible. So, I have a edge from 3 to 5, and 5 to 1 and 5 to 2 is already there, right. So, from similarly from 4 I have a edge to 1, 2 and 5, 1, 2 is already there. So, I have a edge here. So, that is complete the compatibility graph, right. So, this how I can construct a compatibility graph from a given schedule. Okay. So, similarly, I can define the concept of conflict graph. It is just the complement graph of the compatibility graph, because here we are going to define the conflict. If there are two operations which is scheduled in the same timestamp, that means they are conflicting each other, right. So, that means I cannot schedule them into same time. So, what I am going to do in the conflict graph, I will have the same, again it is a consist of set of nodes and the edges. The nodes represent the operations. So, there are 5 operations. So, I have 5 nodes, and if 2 operations are scheduled in the same time stamp and of same type, then I have a edge from between them. So, here I have edge between only 1 to 2 and 3 to 4, right. So, I have edge from 1 to 2 and 3 to 4. And if you just take this graph and you do a complement, you know what is complement graph is, I will have the same nodes, and whatever the edge is missing here, I will add them, right. So, here if you see in this node of 5, only this 1 to 2 and 3 to 4 is missing. So, that 2 edge will be in the conflict graph. So, I can either construct this conflict graph directly from the scheduled behavior, or if I have given the compatibility graph, I can take the complement of that graph and which will be the conflict graph. Okay. So, this is how from the given schedule I can construct the compatibility graph or conflict graph, but what is the use of that? We do not know, right. So, our objective is to identify the minimum number of resource and the binding, and which is something we have not discussed yet, right. So, but we only just argued that given a schedule I can construct a compatibility graph and conflict graph. Okay. So, here I give a formal definition of the compatibility graph, that its graph is consists of G plus consists of V and E, where V is the set of nodes which is represent the operations and which has a 1-to-1 correspondence to the operations, and the edges is representing from Vi to Vj denotes the compatibility operation pair. So, if the operations are compatible, I am going to add a edge in the graph, and we have already discussed in the previous slide. So, what I am going to argue now, that this resource allocation and binding or the resource optimization problem can be modeled as click cover problem in the compatibility graph. So, let us understand why I am telling that, right. So, what I have discussed so far in the compatible. So, if 2 operations they are in different time stamp, that means they are compatible to each other. What does it mean? So, these 2 operations can be mapped to same FU. So, what about 3 operations? If there are 3 operations and they have a edge between all them, that means they are all compatible to each other, right. So, once they are all compatible to each other, that means I can assign all these 3 operations into a single FU. Similarly, for 4, if there are 4 nodes are there, only when they have all edges, right. So, they are all compatible to each other, then I can assign all these 4 operations into a single FU, and I have already discussed for 3. So, similarly, I can talk about 4, 5 and 6 and so on, right. So, what I understood here, if these 4 nodes form a complete graph. So, this is a complete graph, right. Then that particular subset of the graph is compatible to each other and then can be mapped to a single FU. So, but in the whole graph there are say n nodes and this is only 4 nodes. So, this is a complete subgraph, and what does it call? That is called maximal click, right. So, this is a click is a complete subgraph in a bigger graph, right, because I have a graph of n nodes at 20 nodes, and out of that I found that there is a big 4 nodes which form a complete graph. So, this is a complete subgraph or click. So, this as I argued that this once I found a complete subgraph or a click, that can be mapped to single FU, right. So, in the compatible graph, if I identify all such subgraphs, because each of them is, this is FU1, this is FU2 and say this is only 2 nodes I found. So, this is FU3, right. So, what does it mean? I identify the maximal possible subgraphs, complete graph in the compatible graph, and each of them can be mapped to a single FU. So, what I am doing here? I want to cover all the nodes of the graph using this click, right. So, what does it mean? This is a click cover problem, right. So, it is a click cover problem. That means, I want to cover all the nodes of this compatibility graph using such maximal click such that all the nodes are actually subset of one of them, and there will be no overlap, right. So, one node if occurs in one click, it should not occur in other clicks. So, it is independent, right. So, each subgraph is independent. So, if I identify such subgraphs, and then that each of the subgraph is one FU. So, that means identifying, so the allocation and binding problem of FU maps to the click cover problem, right. So, what is that? We will construct a compatibility graph, and then I try to find out iteratively the maximum possible subgraph which is complete, which is a click, and each of them will be mapped to a single FU, and all the nodes inside that subgraph will be mapped to that same FU. So, I will identify the number of FU needed, because each click represent one FU. So, the number of click needed to cover all the nodes define me the number of resource needed, and how the binding will happen. Inside one subgraph, whatever node present there, they will be mapped to a same FU. So, what we understand from this slide, that this allocation and binding problem is nothing but constructing a comparative graph and identify the clicks which will cover all the nodes, which is a click cover problem. So, that means I have reduced that allocation binding problem into click cover problem. Okay. So, similarly, let us understand the conflict graph. So, this is, I know this graph is complement of this compatibility graph. That means, if there is a edge between two nodes, that means they are not compatible to each other, they cannot be mapped to a single FU, right. And this is so they are not compatible when they have conflict, right. So, formal definitions here. So, it is a G minus graph, where each node again represent the operations, and edges denotes the conflicting of pair, right. So, if the two operations are conflicting to each other, I will have a edge there. Okay. This is understood. Now, I am arguing that this resource allocation problem, this resource sharing problem is nothing but graph coloring problem for this conflict graph. So, let us understand why. So, in this particular conflict graph, if there is a edge, that means they cannot be mapped to same FU. But if what about the other thing, if there is two nodes, they have there is no edge between them, I can assign them to a same FU, because there is no edge between them. So, what about 3 nodes who have no edges between them? So, this is one part. Similarly, what about say 4 nodes where there is no edge between them, or say 2 nodes where there is no edge between them. So, what this called? This is called independent set, right, because these nodes are independent to each other, there is no conflict among them, and this particular set of nodes can be mapped to same FU. So, similar to the previous problem, if earlier I have tried to find a complete graph, here I am trying to find out the independent set, that means the nodes that do not have any edge, because this is a complete graph, and if there is no edge, that means they are compatible to each other. So, I can assign them into different FU. So, this can be FU 2, this can be FU 3, right. So, you know what is coloring, graph coloring problem, right. So, the graph coloring problem is what? I have given a graph, I want to assign the color to the nodes, such that if there are 2 nodes which have a adjacent to each other, have a different color. 2 node who they are adjacent to each other cannot have the same color, they should be assigned to same different color, and my objective is to use the minimum number of color to color all the nodes of the graph, right. So, what will happen to this node which are independent? Since they do not have any edge between them, I can put a same color for them. So, I assign blue to them. Since this set they do not have any edge between them, I can put another color, same color to them. So, I put say red to this, and since this nodes they do not have any edge, I can actually assign same color which will not violate my coloring problem. So, I say I assign a green here. Okay. So, what does it mean? And now my objective is what? My objective is to use minimum number of color. So, what is my objective? I try to find out the maximal independent set, right. I try to find the bigger independent set, so that I can put a same color to all the nodes, right. So, this problem now reduced to identifying the minimum color needed. So, identifying such independent set and you put a color to them, and each color now represent a resource, right, one unit of FU, and the nodes that have the same color we can be mapped to the same FU. So, now you understand that once I construct the complete graph, the complete problem now reduced to coloring the nodes of the graph such that no two adjacent node have the same color, and then the number of color needed represent the number of FU needed for me, and each color represents each FU, and the nodes that has the same color can be mapped to a same FU. So, what I understood from here? I understood that this resource sharing or allocation and binding problem can be mapped to as a graph coloring problem. Okay? Interesting, right? So, let us take an example. So, say I took the same example again, and this is my complete graph that we have already drawn earlier, and this is the coloring, right. So, what I am doing here, say these 3 nodes, this 1, 3 and 5, they form a independent set, maximally independent set, because there is no edge between 1, 3 and 5, and I can put them same color, say blue, and this 2 and 4 is another independent set where there is no edge between them, and I put same color to them. So, what does it mean? This is one FU, this is one FU. So, this is LU 1 where operation 1, 3 and 5 going to execute, and this is FU 2 in which operation 2 and 4 is going to execute. So, this is graph coloring problem. Similarly, if you consider the compatibility graph, what I have told, I have to find out the clique. So, you see here this is a clique, right. So, this is a clique of 3 nodes, right, 1, 3 and 5, this is a complete subgraph, and this is the maximal possible clique. I cannot have a clique or a complete subgraph using 4 nodes in this graph. So, I can actually put a same color, or I can actually put this all this clique into FU 1, right. And similarly, this is another clique of 2 nodes, and I can actually assign them into a different FU, right. So, this is my FU 2. So, both gives the same solution. So, either you take the comparative graph and you identify the cliques, or you take the complete graph and you try to color them and you have the same solution. So, this is the clique 1, this is clique 2, and one clique represent one FU, and allocation and binding is done. Okay. So, what we understood, summarize the discussion so far is that let us the problem of doing this allocation and binding is nothing but identifying the compatibility graph and do the clique coverage problem, or you construct the complete graph and you identify the graph coloring. What is the chromatic number is the minimum number of color needed, right. So, identifying the minimum color needed to color the graph is nothing but this chromatic number, and this minimum number of such color is the FU, and similarly minimum number of cliques is the number of FU needed. So, this is how I map this allocation binding problem to either clique cover problem or finding the chromatic number of a graph. Okay. But the problem of these two is well known to be NP complete problem. Okay. Both the problem clique cover problem or chromatic number finding or graph coloring problem is actually known to be NP complete problem. What does it mean? For a generic graph, it means I do not have a polynomial time algorithm to solve this problem. So, that means I do not have an efficient algorithm to solve this problem. If I have to go for a optimal solution, I have to run for a exponential algorithm, either 2 to the power n and on, right. So, it should be a exponential algorithm to solve this problem. So, usually for such NP complete problem, what we do, we usually apply heuristic algorithms, right. So, the heuristic algorithm is something works in a logic that most of the time it gives a optimal solution, and most of the time it gives a good solution. It may not be the optimal, but it is a good enough, right, but it is very fast, right. So, we will learn in this subsequent classes how to solve this either this graph coloring problem or clique cover problem heuristically, but in today's discussion we try to figure out a subset of the graph for which this problem is actually polynomial time solvable. Okay. So, what I conclude here that in general this problem is NP complete problem, but if the graph satisfies a certain property, then this particular problem is actually polynomial time solvable. So, we will discuss in the rest of the class what is the subset for which this problem is actually polynomial time solvable. In the subsequent classes we will discuss the generic solution. Okay. So, let us understand some basic terminology in the graph theory, and we will try to define what is perfect graph. Okay. So, we first try to define a terminology called clique number. So, I told you that a clique is nothing but a complete subgraph. So, this is a complete subgraph of 3 nodes and its clique number defines the number of nodes present in this, right. So, the clique in the omega of this graph is 3. So, this is a graph with complete graph with 4 nodes, right. So, this the omega is 4 of this graph. So, the clique number says the number of nodes present in that particular maximal clique. Similarly, I told you the independent set, the set of nodes that have no edge between them, that is called independent set, and I define a term called alpha g, the number of node present here. Okay. So, the again for this independent set alpha is 3, for this set the alpha is 4. Okay. Now, let us try to understand what is the relation between this alpha and the clique cover number, which is k of the G plus the graph, and what is the relation between omega and the chromatic number x of a graph G minus. Okay. You try to understand one point here. So, if I told you that this if there are 4 nodes in the independent set in a graph, what does it mean? They cannot form any clique. So, they must go into different clique, because you cannot have a clique considering them. So, you need at least, if you have a maximal independent set which is basically have say 4, that means you need at least 4 number of clique to cover them, because you cannot have a clique which will cover 2 of the nodes from here, because there is no connection between them. So, they will all go to different clique. So, what does it mean? So, if I have found a maximum independent set, then the number of clique must be at least this number, right. So, you can have more, but you cannot have less than this, right. So, this alpha, so that means this k should be greater than equal to alpha, right. And similarly for chromatic number, so if I found a maximal clique of size 4, what does it mean? They are all connected, and I have to must assign different color for all these nodes, because they have all edge between this, right. So, this is my color 1, 2, 3, 4. So, if I found a maximal clique of size 4, that means I need at least 4 color. I might need more than 4 because of the other part of the graph, but at least 4. So, what I can say that x must be greater than equal to omega. Okay. So, that is what I told here, that this chromatic number should be less than omega, and this clique cover must be greater than equal to alpha. But in a perfect graph, this relation become equal. Okay. So, in the perfect graph, this the number of color needed to color the graph should be equal to this clique number. So, the maximum number of nodes here. So, this will be equal, and similarly, so the maximum size of the independent set, this alpha should be equal to this number. Okay. So, then I will say this is a perfect graph. Okay. So, this is the definition of perfect graph. Now, we will come to another kind of graph which is called chordal graph, and this is a subset of perfect graph. So, the chordal graph is something is a graph where if you consider a cycle of size 4, that means you have at least 4 edges in them, then you should have a chord. Okay. So, in this is a chordal graph, because it has only one cycle and the cycle have a chord. Okay. So, this graph is not a chordal graph. So, this is also chordal graph, because you have whenever you have a cycle of size 5, you have a chord there, but this is not a chordal graph, because this has a cycle 4, but it has no chord here, right. So, then I will say this is a chordal graph if for any such cycle of size 4 we have a chord, right. So, this is also a chordal graph because there is no cycle, right. So, this is also a chordal graph because there is no cycle of size 4, then still, and although there is no chord, but because there is no cycle of size 4, this is also a chordal graph. Okay. So, what I understand, so the chordal graph is something subset of perfect graph, right. So, chordal graph is subset of perfect graph, and perfect graph is basically subset of generic graph, right. And then I will define another class of graph which is called interval graph. Again, this is a subclass of chordal graph, and this particular graph is very interesting in our context, because what does this graph says. So, I have a graph and I can actually map this node to some interval. Say suppose I have this graph, I have this graph, and then I can define some intervals. So, this is the intervals. So, this is my node 1, 2 and 3. So, 1 is say interval is this, and so 2 is overlapping with say this is my say 2, this is my 1, this is 2 and this is my 3, right. So, I can map these nodes to some interval such that if this 2 node has a edge, their interval will overlap. So, I have a edge between 1 and 2. So, 1 and 2 interval is overlapping, right. So, this is say you can actually think about this is a time, right, and 1 and 3 also have a edge. So, they are overlapping, 1 and 3 is overlapping, right, but there is no edge between 2 and 3. So, this 2 and 3 must not overlap. If they overlap, then they does not hold. So, given a chordal graph, if I can map this node to such intervals such that whenever there is a edge, the corresponding interval will overlap. So, then I will say this particular chordal graph is interval graphs, right. So, I found this interval graph is a subset of a chordal graph. Okay. So, why this particular interval graph is so important? Because for this interval graph, this graph coloring problem is polynomial time solvable. So, if I found that a particular subcases this graph, that complete graph that we obtain is actually a interval graph, then I can actually have a efficient algorithm, or I can solve the, I can actually color the node using polynomial time. Okay. So, this is very interesting. So, let us understand that. So, why this problem is important, because in this case this particular graph is polynomial time solvable, graph coloring problem is polynomial time solvable, right. So, the question here is that how do you identify a graph is interval graph or not, because this is not so easy, and sometime for example, if you have in some cases probably it is not possible to map them into these intervals, right. So, the question here is how do you identify a particular graph is interval graph or not, because if I identify this graph is interval graph, then can I actually solve this problem easily or efficiently. Okay. So, for that let us try to understand another class of graph which is called comparability graph. In this graph, so this is what you have a graph, and so far you understand this, all this complete graph and compatibility graph is actually undirected. Now, I want to orient the edges, that means I want to add direction to the edges. So, I want to make this undirected graph into directed graph such a way that it holds the transitivity property. What does it mean? So, I have this graph, we already know is a chordal graph. So, we have seen that because there is a cycle of 4 and we have a chord here. Now, I want to give direction to these edges, right. So, I have given say direction like this, for this I have given a direction like this, and now see I have a edge I to j 1 to 4 and 4 to 3. So, I must have a edge from 1 to 3 and which is there. So, I have a edge from 1 to 2, I have a edge from 2 to 3 and I have a edge from 1 to 3. So, this is holding the transitivity property. So, that means this is a comparable graph, but if you give the direction like this, so it is not holding the transitivity, because you see here I have a edge from so I have a edge from this and this, and so I have a edge here. So, I have a edge from this, yeah. So, I have a edge from this, and then I should have this edge not holding the property, right, because then I have a edge here I2k. So, I must have a edge here which is not there. So, this is not the orientation, correct orientation, but this is the correct orientation. So, given a chordal graph, I can try to give the direction, and if this particular direction holds the transitivity property, then I will say this is a comparability graph. Okay. And why does it help? This particular theorem actually tell us how this is helpful for identifying the interval graph. Okay. So, I will say an undirected graph is interval graph if and only if it is a chordal, that means it is a chordal graph and its complement is a comparability graph. So, this theorem says that if I identify a graph which is called chordal graph and I take the complement of the graph and I identify that is actually comparable graph. That means, in that particular graph I can give this and I can make this a directed graph which holds the transitivity property, then my graph is actually interval graph. Okay. So, this theorem give us the solution that if you try to identify a chordal graph and then it take the complement and check whether that graph is comparability graph or not. If it is that, then I can ensure that this particular graph is as well interval graph. And if I try to solve this problem for this graph coloring problem for this, I can solve it in efficiently, that means in polynomial time. So, now let us go back to our this data flow graph things. So, once if you remember for the scheduling, we have seen that we have taken one basic block at a time and then we try to schedule the behavior. And but in general, now if you try to solve this allocation and binding problem for the particular basic block, we will show that that particular graph is actually nothing but interval graph. Okay. But in general, whenever you have a function call and then if else loops and all, that problem is not polynomial time. Okay. And or the complete graph that we are going to construct will not satisfy the interval graph property. But for this only for a basic block or a single block, the comparative graph, that complete graph will be is interval graph. Okay. So, that is where this particular property holds. So, for a if we try to solve this allocation and binding problem for a specific block or a basic block, I can solve it efficiently. So, let us see how. So, I can actually apply this left edge algorithm, which is a polynomial time algorithm for this to solve this problem. Okay. So, let us take an example. So, I have this schedule which we have taken in earlier classes as well. So, now you see here I am going to construct, this is for multiplier and this is for ALU. So, here what are the multiplication operation 1, 2, 3, 6, 7, 8, right. So, I have these nodes here, and what are the ALU operation 10, 11, 4, 5 and 9, right. So, these are the operations for the ALU. So, these two are different problems. So, let us consider this one first, and I can actually, so this is my compatibility graph, right. So, you see here, so 1 will be compatible with 3, 6. So, these are my multiplication operation, right. So, this 1 is compatible with all operations which is scheduled in different time steps. So, 3, 6, 7, 8. So, 1 has a edge to 3, 6, 7 and 8. Similarly, 2 have a edge to 3, 6, 7, 8, you can check it here, and this way I can actually construct the compatibility graph for this, right. And similarly, for the ALU, this 10 is actually compatible with 11, 9, 5 and 4, right. So, 10 is compatible with 9, 4, 11 and 5 and so on. So, I will construct this, and now you see the complete graph, right. So, you can take the complement of this graph. So, I will construct the complete graph here. So, it has 1, 6, 8, 2, 3 and 7. So, what is the complete graph here? 1 and 2 is conflicting. So, 1 with 2, 3 and 6 is conflicting, 3 and 6, and 7 and 8 is conflicting, 7 and 8. So, this is my complete graph. Okay. So, this graph is actually I am telling that this is interval graph, and because its complement graph is this, which is compatibility graph, and this is actually comparable graph, because I have given the orientation of the edges, you can note say here. So, you consider any such transit. So, I have a 2 to 6, I have 6 to 8. So, I have a edge from 2 to 8. So, I have a edge from 1 to 3, I have a edge from 3 to 7. So, I have a edge from 1 to 7. So, this you can cross check. So, for example, I have a edge from 2 to 3, I have a edge from 3 to 7. So, I have a edge from 2 to 7 as well. So, the transitivity property hold in this particular graph. Okay. So, I will say this is a chordal graph, because there is no fourth cycle and there is no problem of chord. So, this is a chordal graph, and the implement this complement graph is a comparable graph, and hence this is a interval graph. And we will argue that I can actually map these nodes into some interval such that whenever there is a edge between them, their interval will overlap, and when there is no edge, their interval will be non-overlapping, right. And how I can do that? That actually can be done easily. So, this is my schedule, and what I am going to do is, wherever the operation schedule, I will construct an interval for this. So, for the interval of this nodes is this, right. So, I am only considering the multiplier now. So, these are the intervals. So, if the one operation is a multi-cycle, so I have an interval more than one cycle, right. So, some operation is a 3 cycle, the interval will be 3 cycle, but the schedule that I have considered here is only a single cycle. So, this is how I have actually constructed the interval, and now see this 1 and 2 is overlapping. So, their interval is overlapping, 1 and 3 is not overlapping, they are in different time steps. So, their interval is not overlapping, 3 and 6 is overlapping. So, their interval is overlapping, 7 and 8 is overlapping. So, these are the only 3 overlaps and there is no other overlaps, right. So, this shaded nodes are for multiplier and the other are for ALU operation. So, let us keep that because this 4, 5, 9, 10 is for operation ALU and I will consider them separately, right. So, this is my interval graph, right. So, this is my intervals and which actually satisfy my the edges requirement of the interval graph, right. So, this is how I argued here that once I consider a graph of only for this a single basic block, my complete graph is actually a interval graph and the corresponding interval I can construct this way, because I can construct the interval easily from the schedule behavior, and its complement graph is basically nothing but a comparable graph that I have already shown. So, I can actually efficiently solve this graph coloring problem for this complete graph in polynomial time, and for that there is a very well known algorithm called left edge algorithm, and I am going to cover that algorithm in the next class. Okay? Thank you.